Data structures are the hidden architecture of software. They decide how data is stored, how quickly it can be accessed, and how efficiently it can change. In this video, we will build a visual mental model for the most important data structures in computer science. An array is a fixed size, ordered collection of items. Every item sits at a numbered position. Because the items are stored right next to each other in memory, the computer can jump directly to any index. Finding item number 40,000 takes the same time as finding item number 4. That is constant time access. But arrays have a major trade-off. Their size is fixed. If you insert an item in the middle, the computer must shift every item after it one position forward. So arrays are blazing fast for reading, but rigid when data keeps changing. A linked list solves the rigidity problem of arrays. Its nodes do not need to sit next to each other in memory. Each node stores a value and a pointer to the next node. To insert a new node, you do not shift thousands of items. You simply rewire 2 pointers. But flexibility has a cost. A linked list cannot jump directly to an index. To find an item, it must start at the head and follow the chain one node at a time. A long list may require thousands of steps. A stack follows last in, first out. Think of a stack of plates. You push onto the top, and you pop from the top. You never touch the middle. That restriction makes push and pop constant time. A queue flips the logic. It follows first in, first out, like a line at a coffee shop. You in-queue at the back, and dequeue from the front. The oldest item is served first. A Deque is a double-ended queue. Both ends are active. You can add or remove from the front, and also add or remove from the back. It can behave like a stack, a queue, or something more flexible than both. A hash map stores key-value pairs. When you search for a key, the key goes through a hash function. That function converts the key into a slot number. So instead of scanning everything, the computer jumps directly to the correct slot. A hash set is like a hash map without values. It only stores keys. Its job is to answer one question extremely fast. Is this item present or not? That makes hash sets perfect for membership checks and duplicate removal. A tree is a hierarchy. There is one root at the top, branches below it, and leaves at the bottom. File systems, HTML documents, comment threads, and decision trees all naturally fit this parent-child structure. A binary search tree adds one powerful rule. Values smaller than a node go left. Values larger than a node go right. During search, each step eliminates an entire half of the remaining tree. A heap is also tree-based, but the goal is different. A heap always keeps the highest priority item at the top. In a max heap, the largest value rises to the root. In a minute heap, the smallest value rises to the root. That is why heaps power priority queues, schedulers, and shortest path algorithms. A graph is made of nodes and edges. Unlike trees, graphs do not need to be clean hierarchies. They can be messy, cyclic, directed, undirected, and deeply connected. Social networks, maps, web links, recommendation systems, and network routing are all graph problems. A tree is a tree built for prefixes. Each level represents one character in a word. When you type A, then P, the structure already knows which branch you are following. That is the magic behind autocomplete, spell check, contact search, and dictionary prefix lookup. A disjoint set, also called union find, tracks which elements belong to the same group. Every element starts alone. When two elements become connected, their groups merge. To check if two elements are connected, you only compare their group representative. A Bloom filter is extremely fast and memory efficient, but it can occasionally lie in one direction. If it says no, the item is definitely not present. If it says yes, the item is probably present. That makes Bloom filters useful for quickly ruling out obvious misses before expensive lookups. LRU Cache stands for least recently used. When memory is limited, the system keeps recently used data near the front. When new data arrives and the cache is full, the least recently used item at the back is evicted. This is usually built with a hash map plus a doubly linked list. Arrays, linked lists, stacks, queues, Deques, hash maps, sets, trees, heaps, graphs, tries, union find, Bloom filters, and LRU caches. Each one is not just a definition. It is a trade-off. When you understand the trade-off, you understand why software is designed the way it is.